17 of our logic curriculum. Today we're going to be taking a slightly different bent, and we're going to be talking about set theory. And so what I want to do to start is go back to what we were dealing with our predicate statements. So I've got 5 statements here. I've got 2 as an even number, 4 as an even number, 6 as an even number, 8 as an even number, 10 as an even number. And the thing I notice is that all of these statements have is an even number as a part of it. So let's go ahead and let E represent the predicate is an even number. So I could write this statement as E2 because 2 really is the subject of our statement. And similarly, I could write this as E4, E6, E8, and E10. In other words, 2, 4, 6, 8, and 10 all go with this predicate. And so what I can do is I can kind of write it together as one set of subjects, a set of subjects that goes 2, 4, 6, 8, and 10. This set of subjects goes with a predicate E, where E represents is an even number. So, I want to talk about some basic definitions. A set is a collection of objects that satisfy a given rule. And so what I had here is I had my given rule was that it had to be an even number. And 2 is an even number, 4 is an even number, 6 is an even number, 8 is an even number, 10 is an even number. So this is my set E. E represents the rule is a given number. And each one of these subjects, each one of these objects in the set is called an element. An element is an object in a set. Now we're going to be using capital letters for sets, just like we used capital letters for predicates. But if I want to talk about an element in a set, I'm going to use this symbol that kind of looks like a C with a horizontal line in it. Some people think it looks like a letter E. Some people think it looks like the euro symbol for the euro, the currency that's used in Europe. And this is the symbol that we'll use whenever we're talking about an element. So I could say that 2 is an element of set E. I could talk about 4 being an element of set E. But 7 is not an element of set E. So I use that element symbol with a slash through it to denote that it's not an element in that set. So I want to talk about a few sets here. The first set we have is set E, which we've already touched briefly on. It contains 2, 4, 6, 8, and 10. And my given rule here is that these are even numbers. So I have a set called O, and you've probably surmised that O represents odd numbers. So I'm going to put 1, 3, 5, 7, and 9 into that set. I've got P, and I'm going to let P represent my prime numbers. So the prime numbers that are less than or equal to 10 would be 2, 3, 5, and 7. And I can talk about composite numbers as well. Those are the numbers that have more than 2 distinct positive factors. So I could talk about 4, 6, 8, 9, because 9 is 3 times 3, and 10. So I've got these different sets. Each one of these sets have elements in them, objects that satisfy that given rule. So a universe set is a set that contains all possible elements. So my universe is everything. My universe is all of the elements that we are possibly going to be considering. And so if I go to the example of the sets that we've talked about so far, my universe has got to have a 1 in it, because 1 is one of the elements that we're looking at. It also has to have a 2 and a 3 and a 4, because I see those in the different sets. 5, 6, 7, 8, 9, 10. So my universe set is containing all of these elements. My universe is everything that we could possibly choose from. So remember that when we are talking about quantified statements, where I would talk about searching the entire universe, looking for a dog that had fleas, or looking for a cat that had whiskers, when I wanted to say all dogs had fleas, or some dogs had whiskers, this is my universe. This is what I'm searching for. And when I want to say all even numbers, something is an even number, these are what I'm choosing from. Well, 2 is an even number, 4 is an even number, 6 is an even number, 8 is an even number, 10 is an even number. All of those are going to be elements in that set E. A complement is a set that contains all elements not found in a given set. In other words, I'm going to be looking at my universe, and I'm going to say, what in my universe is missing? And I can make a completely new set out of this complement. This complement is almost like the negation that we were talking about back when we were talking about basic statements, because these are elements that are not in the set. So, if I want to know what's not in E, I'm going to take a look at my universe and see what's not in set E. Well, 1 is not in set E. Neither is 3. Neither is 5, nor 7, nor 9. So I've got this set that's the complement of E. It kind of goes with E together to make the entire universe. But it's a set of everything that's missing from me. These are all of the is not an even number. Now, if you notice, that looks suspiciously like this set here. O contains 1, 3, 5, 7, and 9. And so there are some situations where we'll see that the complement of a given set is another one of our given sets. And of course, if we asked for the complement of O, everything that's not in O, that would be 2, 4, 6, 8, and 10. But if I ask for the complement of P, what's missing from P? A 1, a 4, a 6, an 8, a 9, and 10. Those are the elements of my universe that were missing from P. And notice that it's not exactly the same as my set C. And that's because 1 is a number that is neither prime nor composite. A prime number has to have exactly 2 positive integral factors. A composite number has to have more than 2 positive integral factors. 1 only has 1 factor. It's equal to 1 times 1. It's equal to itself times itself. And so this complement of P is not the same as C. And similarly, the complement of C is everything that's not in C, which is 1, 2, 3, 5, and 7. In other words, everything that was in P plus the aforementioned 1. When I'm talking about a universe set, my symbol for a universe is a capital cursive U. And when I'm talking about a complement, my symbol for a complement is a capital cursive C. And so that's why I'm using these different fonts when I'm talking about the universe or when I'm talking about complements. There are other things that we can do with sets. We can put them together or take them apart. And so I want to talk about two ways that we can put sets together. So I've got a union, and a union is a set that contains elements found in one of two sets. In other words, it can be in one set or the other set or both sets. And if that sounds a little familiar, it sounds like it can be in one set or another set. That means this union is very closely related to a disjunction. As a matter of fact, the symbol for a union is a U, in the same way that the symbol for a disjunction is a V. And if you guess where I'm headed here, an intersection is going to have to deal with an and its symbol is going to be an upside down U, just like the symbol for a union. I mean, just like the symbol for a conjunction was an upside down V. An intersection is a set that contains elements found in both sets. Not one or the other. They have to be in both sets. If they're not in both sets, then they can't be in my intersection. And so what you'll notice is that unions tend to be bigger, and intersections tend to be smaller. And I say tend because it's not 100% of the time, but it's something that we see enough that it's important to remark upon it. So I've got these same sets that we've talked about: the evens, the odds, the primes, and the composites. And I've got a set called even union primes. In other words, the elements that are in one or the other or both. Well, 2 is in one or the other. In this case, it's in both. So is 3, it's in P. 4 is in E. 5 is in P. 6 is in E. 8 is in both. Excuse me. 7 is in P. 8 is in E. And 10 is in E. Notice the numbers that I'm missing is I'm missing the 1 and I'm missing the 9 because neither of those numbers are even. Neither of those numbers are prime. So it's one of those situations where it's false for the first set and it's false for the second set, and a disjunction is a set that's only false if two given statements are false. It's not in the first set and it's not in the second set. So that's why 1 and 9 are missing. If I look at O union P, I'm looking for the elements that are in one or the other or both, and that's going to give me 1, 2, which I get from P. 3 is in both, 5 is in both, 7 is in both, and 9 is only in odds. So I end up with a set. By the way, notice this set has 6 elements in it. It's bigger than the 2 sets that we were considering. And we notice that unions tend to be larger than the sets we're dealing with. And I mention that because when we're doing the intersection, I want you to notice that they tend to be smaller. So I've got O intersect P. I want the elements that are in both of these sets at the same time. And the only numbers that are in both of these sets are 3, 5, and 7. O has a 1 and a 9 that doesn't show up in P. And P has a 2 that doesn't show up in O. So notice that this 3 element set tends to be smaller than these 2 sets that were given to us. And if I look at a set like P intersects C, I run into an interesting issue. What elements are in both P and C? What numbers are both prime and composite? And notice that they share no elements. We say sets that share no elements are called disjoint. And their intersection is an empty set. And so I'll often write just empty braces like this, but you'll often see other mathematicians use a circle with a slash through it to represent the empty set. Please do not try and use both. This is bad. Please don't do that. So notice that my unions tend to be bigger, and if I chose my sets wisely, I could end up with the entire universe. If I tried to put E with O together as a union, I'd end up with the entire universe because they'd take care of 1 and 9 for me. So my sets can be as big as the universe. My sets can be as small as a set with nothing in it, an empty set. And so those are two things that we can do with unions and intersections. Remember that unions and intersections are like my disjunctions and my conjunctions of logic. The next thing I want to talk about is the subtraction. A subtraction is a set that contains elements. Found in the first set. And not found in the second. And here, order matters. It's important to note which one comes first. In our prior example, it didn't matter if E came first or P came first, because we're kind of just smushing these sets together to make a larger set. Similarly, it didn't matter which one came first, O or P, because we're only seeing where those two sets overlap. But when I talk about this set subtraction, the order does matter, because there is a difference between taking O and taking away the elements of P, and having P and taking away the elements of O. If I start off with O, I'm starting off with these numbers, and I'm taking away what P has. So I'm taking away a 2. There's no 2 to take away. I'm taking away a 3, so that's gone. I'm taking away a 5, so that's gone. I'm taking away a 7, so that's gone. And so the only sets that I have left, the only contents in this difference, are 1 and 9. So my set has got to contain the elements 1 and 9. That's if I started with O. But if I started with P, I'm starting with this set and taking away the things that show up here. So I'm taking away a 1. There's no 1. I'm taking away a 3, so that's gone. I'm taking away a 5. I'm taking away a 7. I'm taking away a 9, but there's no 9 to remove. This time, because I started with P, all I'm left with is a prime number that's not odd. Just like up here I have odd numbers that aren't prime. Order matters. So let me do the same thing down here. If I was to take C minus E, I'm starting with these composites and taking away the even numbers. That means I'm only going to be left with the element 9 in my set. Now notice I still have a set. A subtraction is a set, so I still have to draw those braces. But it's a set containing only one element. If I try and do C minus 0, if I do C subtraction 0, C subtraction O, I mean, I'm going to remove all of the odd numbers, which means I'm only getting rid of the 9. This ends up being 4, 6, 8, and 10. It is possible through subtraction to completely get rid of all the elements, leaving us with an empty set. It's possible to subtract elements that aren't in the first set and therefore end up with our original first set as our answer. But in general, set subtraction tends to give us smaller sets. Notice that what we're doing is that we're saying that it's in the first set and not in the second set. So we do see a lot of the relationship to the conditional that we were talking about with the predicates before. That TF being where it's false. Those TFs are the ones that we're getting rid of. So again, I'm seeing a lot of parallels between negations, conjunctions, disjunctions, conditionals, those terms that we learned at the beginning of this course. I'm seeing those go throughout this set theory that we're talking about. So, I want to do one last example here. So, I've got a set. In this set, my universe is red, orange, yellow, green, blue, indigo, violet, black, and white. I've chosen some of the Crayola colored boxes. I'm not choosing all of them. But I have two sets here. I've got one set, red, white, and blue. The rule here are the colors of the American flag. And here I've got red, orange, yellow, green, blue, indigo, violet. These are the colors of the rainbow. And so I want to come up with some sets here. So the first set I want to come up with is the complement of R. Remember, a complement is a set that contains all elements not found in a given set. So what's not in R? That's in our universe. Well, red, orange, yellow, green, blue, indigo, and violet are already taken up. But black and white are missing. So my complement is going to contain black and white. And similarly, if I try and do the complement of A, I want everything that's not in A. So orange would work. So would yellow. So would green. Blue shows up, so I can't include it. But I'm good with indigo and violet. And black. But white does show up. So I had to get rid of those three elements from my universe to find my complement. If I want to find the intersection, I want to know, what do these two sets have in common? What's in both sets? Remember, intersection is like my and. It has to be in one set and the other. And the only elements that are in both are red and blue. Those are the only elements that are in both sets. If I go down here and do a union R, remember, union is like a disjunction. It's in one set or the other or both. So red will work, orange will work, yellow would work, green would work, blue would work, indigo, violet, and white. As a matter of fact, the only element that we're missing is black, because black shows up in neither of these sets. And the last example I want to do is set subtraction. That's everything that's in my first set that doesn't show up in my second set. So, red's in my second set, so I have to strike it from the first set. Orange, not a problem. Yellow's not a problem. Green's not a problem. Blue is a problem. I need to strike it. Indigo, violet. So taking everything from R out of that set, I'm left with a set that contains one element, the set that contains white. I wanted to do this example because this is an example that doesn't involve numbers. A lot of people think that math has to involve numbers. Math is really a study of patterns. And so we're looking at patterns behind these definitions. So, thank you for watching my video. This is Mr. Potter. Have a great day.